Hi class, we're now in 17.7 base solutions. So the stronger the base, the more it is willing to accept the proton. So it has a stronger attraction to it. So if we use water as a standard acid, then the water, excuse me, then a water will donate a proton because of being the acid, and the base will take that proton. For ionic bases like sodium hydroxide, it completely disassociates because it's a strong base. It's a strong electrolyte. That means multi-hydroxide strong bases completely dissociate in one step. And if we're looking at the concentration of hydroxide ions, we use POH. So weak bases, just like weak acids, only dissociate, only a small fraction of molecules accept a proton, hydronium ions. They are weak electrolyte. Most of the weak base molecules do not take hydronium ions from water, much less than 1% in water. So it's very weak. And the hydroxide concentration is far less than the actual concentration of the weak base. Finding the pH of a weak base solution is similar to finding the pH of a weak acid. So we're going to look at Kb. This is a base strength is measured by the size of the equilibrium constant when it reacts with water. So here we have this equilibrium reaction. The base reacting with water produces hydroxide ions, and the base takes that proton. The equilibrium constant is called the base ionization constant, which is Kb. And if you have a strong base, then you have a very large Kb. And this is how we would set this up. Okay, so here is a list of weak bases, the ionization reactions, and the Kb for these reactions. And if you notice, they have nitrogen in them, which is an amine or ammonia. So you can see a lot of these have a nitrogen, which here's ammonia. Remember, it has to have a lone pair if we're dealing with a Bronsted-Lowry base. And all of these, you can see here, these little flower petals, have a lone pair to take a proton. All right, so finding the hydroxide concentration and the pH of weak bases, we need an equation. So you absolutely have to have a balanced equation, and then you prepare an ICE table. We take that information that we're given and we plug that into the ICE table. Then we can substitute the expression for equilibrium constants into a K expression, determine the hydroxide ion concentration from the X, and then we can calculate the POH. From there we can get our pH. Okay, so let's take a look at a problem. So here we have a balanced equation, and we want to find out the hydroxide concentration and pH of 0.100 molar ammonia solution. So we take our balanced equation, we plug in all of our information here. So we have our initial concentration of our molarity, and then we have zeros because we don't have our hydroxide concentration or our ammonium ion concentration. We're going to plug in for X. So this is 0.100 minus X, and then plus X plus X. So we set it up with the Kb. We're going to square this, and we're going to approximate the X, which means we're going to kick it out. Square both sides in order to get rid of the X squared. And we're going to also test to make sure that the ionization is less than 5%. And it is, then we don't have to bring that X back and do the quadratic formula. So we do. Here's the steps. We square root it. We end up with X as 1.33 times 10 to the 3. And that is, we check the approximation. So 1.33%, it's valid, less than 5. Now remember, this X is the concentration of ammonium ions and hydroxide ions. So we're going to take the hydroxide ion, but this is asking for the pH. We are dealing with a hydroxide. We need hydronium concentrations. pH is related to hydronium concentrations. So we're going to use our Kw and solve for the hydronium concentration. So doing our math, we isolate it. We end up with 7.52 times 10 negative 12 molar. Plug that into the negative log, and we end up with, remember, 3 sig figs, so there's 3 sig figs. We end up with the pH of 11.124. That's it.